All right, let's dive into a technology that sounds like it's straight out of science fiction, but it's actually happening in labs right now. We're talking about quantum batteries. And believe me, they could represent a leap so huge it might just spell the end of charging as we know it. So let's kick things off with a question that I'm pretty sure every single one of us has asked.
We've all been there, haven't we? Just staring at that little battery icon on our phone, willing it to fill up faster. It has to be one of the most universal frustrations of modern life. But seriously, why? With all the incredible tech we have, why are we still tethered to a wall just waiting for our devices to power up? Well, the answer is surprisingly physical. The simple, kind of brutal truth is this. For more than 100 years, every single battery we've ever used works on the same basic principle. It's all about moving physical stuff, matter, from one place to another. And frankly, we've gotten about as good as we can at it. We've pretty much hit a fundamental wall of physics. Okay, so let's break that down. What exactly is this bottleneck? Why are the batteries in our phones, our cars, our laptops, why are they all inherently so slow and honestly pretty inefficient? So inside your phone's battery right now, there are tiny lithium ions, literally, and I mean literally, swimming through this chemical soup called an electrolyte. And just like when you're swimming, that movement creates friction. That friction generates heat, which is exactly why your phone gets warm when it charges. And over time, all that heat slowly wears the battery down. But what if we didn't have to move anything at all? What if there was another way? Well, recent studies are pointing to a completely different path forward, a whole new way of thinking about energy storage. Instead of moving matter around, we can just use light. And this right here illustrates the difference perfectly. The old way is all chemistry. You can think of it like physically filling a bucket with water. The bigger the bucket, the longer it takes. But the new way, it's quantum optics. We are not filling the bucket anymore. Instead, we're using light to change the energy state of the bucket itself. It's a complete paradigm shift. Okay, this is where things get truly mind-bending. Because this new approach, it doesn't just make things a little faster. No, it unlocks a quantum phenomenon that completely shatters the rules of conventional charging. The secret sauce here is a principle called superabsorption. See, in the quantum world, molecules can become what's called entangled. And when they do, instead of acting like a big crowd of individuals, they all start acting as one enormous single superatom. And this collective unit can soak up light energy almost instantaneously. So what does that actually mean in practice? Well, it leads to some pretty incredible math. In a normal battery, the charging power scales linearly with the number of cells. You double the cells, you double the charging speed. Simple. But in a quantum battery, because of that superabsorption thing, the power scales with the number of molecules squared. And here's the crucial takeaway. If you double the size of a quantum battery, it doesn't charge twice as fast. It charges 4 times faster. The bigger you make it, the faster it charges. That is the complete opposite of every single battery we have ever known. Okay, this all sounds absolutely amazing, right? So why don't you have one in your car right now? Well, as with any revolutionary technology, there are some major hurdles. It's time for a little reality check. You see, for a long time, scientists could get the energy in, but they just couldn't get it back out. But a very recent breakthrough, one that research suggests will have implications around 2026, finally changed that with something described as a micro sandwich. It works in 3 steps. First, 2 mirrors trap light. Second, a special organic dye absorbs all that trapped energy. And finally, a layer of carbon is used to coax that stored energy back out as electricity we can actually use. But the biggest challenge, the main villain in this whole story, is something called decoherence. And this is a fantastic analogy for it. Think of a quantum state as a perfectly spinning top. It's balanced, it's stable, it holds its energy. But the tiniest little touch, a bit of heat, a stray vibration, and it starts to wobble and falls over, losing all that energy to the environment. So this creates a very clear trade-off, at least for now. Quantum batteries give us that nearly instant charge speed we dream of, but their stability is super low. They might only hold that charge for a few hours. Meanwhile, your standard lithium-ion battery is slow to charge, but it's incredibly stable, holding its power for months or even years. You know, the best way to think about where we are right now is to call it the transistor phase. Back in the 1940s, the very first transistor was this clumsy, hand-sized contraption. Today, we can fit billions of them on the tip of a fingernail. The physics of quantum batteries has been proven. It works. Now comes the long, hard part, mastering the engineering.
So what does that engineering journey even look like? What's the actual path from a lab prototype today to a world of instant power tomorrow? Well, studies suggest the rollout is going to be phased. You're not going to see these in your TV remote first. Between now and 2030, they'll likely be used to provide super clean, stable power to incredibly sensitive quantum computers. Then, in the mid-2030s, they'll be perfect for things like medical sensors that need a huge burst of power for just a microsecond. And then, maybe by 2040 and beyond, we may finally reach that instant charge world for the rest of us. I think one of the lead researchers really summed up this exact moment perfectly. They said, "We've caught the lightning. Now we just have to figure out how to keep it in the box. We've managed to capture this incredible fundamental power of the universe. The whole challenge now is just containment and control." And that's the thought I really want to leave you with. Just imagine a world where waiting for a charge is a forgotten memory. Electric cars that power up in the time it takes to fill a gas tank. Devices that are constantly powered just by the ambient light in a room. What happens to our world, our technology, our lives, when the very concept of charging becomes instant?